Hi, this is Miss Mantle, and today we're going to be reviewing radicals and simplifying radicals. In addition to simplifying, we're going to be adding and subtracting, multiplying, dividing, and rationalizing as well. So the first thing to know is what are the different parts of a radical. Let's go ahead and zoom in here. So a radical consists of several parts. Typically we have a number in the front called the coefficient, and then we have this like V-shaped thing called the radical symbol. Sometimes people put a little like end here and close it. You don't have to do that. And then the number underneath is called the radicand. Now with the radical symbol, when there isn't a number written up here, then it implies that it's a square root. You could also write it like this. Whoops. You could also write it like this, representing a square root. But the number if there isn't a number that's written in this little area here, then it implies a square root. We're going to see a little bit later in this unit here how to deal with cube roots or fourth roots, and that just means that this number here, the index, is going to change. But for today, we're just going to focus on square roots. Okay, now if there isn't a number in front, meaning no coefficient, it means that there's the number 1. It means that we have the number 1 in front. Like, for example, if I just say like root 3, this implies 1 root 3. Okay, so when we're simplifying or working with radicals, you have to remember some basic information about perfect squares. And so let's just remember or identify perfect squares and then also their square roots. So if we zoom in here to the perfect squares, I'm going to ignore 1. 1 times 1 is 1. 1 is one of those unique numbers, like if I multiply by 1 or divide by 1, I end up with the same number. I think we can all agree that 1 times 1 is 1, and so we don't necessarily have to factor 1 out of anything. But if we have perfect squares that are bigger than 1, then we want to factor them out. So the next biggest perfect square besides 1 is going to be 4, because that's 2 times 2. And you learned these in previous math classes, these perfect squares here. You should know at least, the first 15, I think, by heart. That would be a good thing to know. So I'm just filling these out. 121, 12 times 12 is 144, 13. This is 169. And then the way that I remember 14 times 14 is it's just 196. It's just the reverse of the numbers from 13 and 13. And then lastly, 15, that's 2 something, and then it has to end in a 5. So it's 225. That's a good one to remember as well. Okay, so those are our perfect squares, and those are factors that we're going to be looking for inside our roots as we simplify. So if we move over here and talk about the radicals or the square roots, so I'm thinking about, about this. I want to know what number underneath the square root is going to be equal to 2. Well, we know that 4 is 2 times 2. In other words, 2 squared. And so when we have this expression here with the square root and then 2 squared, the square root and the square are inverse functions. They are functions that undo each other. So think about, like, if I added 2 and subtracted 2, the original number would be the same. Well, the same thing happens here when I square and I square root. This is not really proper notation, but you can kind of think about like the square root and the square kind of canceling each other out. You have to be careful there in some variable cases, which we'll talk about in the future. Anyway, I don't want to spend a ton of time on that, but so if we just kind of work backwards here. The square root of 9 is going to be 3. The square root of 16 will be 4. The square root of 25 is going to be 5. And so we're going to continue on down this path here. And if I can find these perfect squares under the root, well, then that means that we can simplify our radical expression. The square root of 169 for 13, the square root of 196 for 14, the square root of 225. Okay, so now that we've refreshed our mind about our roots and radicals and perfect squares, let's talk about simplifying. So to simplify a root, that means that we want to factor the highest perfect square. Okay, now not in all cases will you recognize that you have a perfect square. Some bigger numbers are a little bit trickier to find the perfect square right away, right off the bat, but we want to try. It's the most efficient way to do it, but when we do some examples today, you'll see that even I sometimes need to use other methods until I can see the perfect square. Okay, so step 1 is to break the number inside the radicand into 2 numbers. The first one being the highest perfect square. So we're going to pull out the square root number, placing it outside and leaving the rest inside. And so, for example, if we want to simplify the square root of 48, your best option is to use the factors of 16 times 3 rather than 8 times 6. So if I can factor into 16 times 3, well, the square root of 16 is 4, and so I take the root of 16 and I pop that out, and then 3 isn't a perfect square, I leave it under the root. Okay, now if you didn't recognize that root 48 had a perfect square of 16 in there, maybe you just, weren't thinking, and you got 8 times 6. Well, you can still get to the same answer. I know that 8 is 4 times 2, and then I know that 6 is 2 times 3. So I have a root 4, but I have another one here as well. So this is like saying 4 times 4 times 3, which is the square root of 4 is 2, the square root of 4 is 2, the square root of 3 is 3, and I can multiply these together on the outside, and I'd still get 4 root 3. So we can go ahead and, like I said, if you don't recognize right away that there's a perfect square inside there, if you work with your prime factors and you start looking for perfect squares or combinations of numbers that give you perfect squares, then you can simplify. So let's go ahead and turn the page. And here we're going to simplify. So we're going to simplify the following in simplified radical form, no decimals. Let's try not to use our calculators as well. Okay, so for the first one, 18. All right, so I know that this is going to be 2 times 9, but I'm going to write it as root 9 times 2. And the reason for that is just that's the way I like to do it. I put the perfect square first. The square root of 9 is 3, and then the root 2 is just left over. And here we are. And that's it. So if we move on to the next problem, I know that 25 is a factor of 75. I think about it in terms of money, quarters. There are 3 quarters in 75 cents. The square root of 25 is 5, so that pops out of the square root, and then root 3. And here's your answer. So I want to mention, when we're doing this, that I'm kind of leaving out a step. What I'm doing here is essentially I'm breaking this apart into 2 separate roots, and then I evaluate them separately. So the square root of 25 I can write as 5. It just, the root goes away, and then the root 3 remains. All right, let's see what's happening over here. 72. Okay, so maybe you know right off the bat what the factors of this are, but let's suppose I don't. Let's say that I'm just thinking about factors. I know that this is 9 times 8, and 9 is a perfect square, and I know that 8 also has a factor that's a perfect square, that's 4, and so I can write this as 9 times 4 times 2. Okay, so then I can treat them separately. The square root of 9 is 3, the square root of 4 is 2, but this isn't 32, this means I'm multiplying, and then I have a root 2 left over. And then I multiply these numbers in the front and get 6 root 2. Okay, now maybe you recognized right off the bat that 72 is actually 36 times 2. That's okay as well. If you notice here, 9 times 4, the two things that were perfect squares, equals 36. So you could have gotten here a little bit quicker if you had recognized that 36 was a perfect square. But, you know, however you get there, it's just more efficient. Notice that there's only a couple of steps here when we factored it in terms of 36 and 2 as opposed to the other method. It doesn't really matter to me. You just want to make sure that you know how to simplify. Okay, let's move down to this next one, 96. Okay, so 96 isn't really speaking to me right now. I do know both of these numbers are divisible by 3, so I'm just going to call that 3 times 32. And 32 can be factored into 4 times 8, but I know that 8 also has a factor of 4, so I think that really means that this can be written as 3 times 16 times 2. You could also just do 3 times 4 times 8 and call that 3 times 4 times 4 times 2. Either one of those are fine. The square root of 16 is 4. Let me rearrange that. 16 times 3 times 2 is 6. So this is going to be 4 root 6. All right, next. 50, and this is a nice easy one. 50 is going to be 25 times 2, and so the square root of 25 is 5. The root 2 will be left over, and then this 3 in the front just carries along, and we multiply them together. We've kind of been doing that in a couple of other examples, so we get 15 root 2. All right, last one. Okay, now root 98. Now we just did root 96, so I know root 98 is not a perfect square, and I know that 16 is not a factor. So, let's see. Let's see here. I know that this is -8, and then 98 is even, so it's going to be 2 times something. So 2 into 98 is 4, 18, oh, good. This is 49. Let me rearrange that. I put the perfect square first, and so then I get -8 times the square root of 49, which is 7, times the square root of 2. So we get -56 root 2. So that's simplifying. So simplifying is probably the hardest thing we're going to talk about today. The next thing is adding and subtracting. In order to add or subtract, they have to have the same radicands. That means they have to have like terms. So if you have radicands that are not the same, then you want to try to simplify. Simplifying first. And so we add or subtract the outside coefficients, leaving the radicals just as they are, just like it says a denominator with fractions, or just like when you have like variable terms. If you did something like, 3x squared plus 4x squared, we write that as 7x squared. We add the coefficients and then we leave the x squared term by itself. Now I realize that we don't have variables under the roots, but we just kind of treat that as like a like term. Okay, so let's take a look at a couple of examples here. The first one is 5 root 7 plus 3 root 7. One of the things that you can do is write it like this. We could say 5 plus 3 and then root 7 if you factor the root 7 out at the end. You don't have to do that, but that's something that sometimes people do. And then this would just be 8 root 7. Number 2, I look at the roots. They have this like terms. The thing I need to remember here is that there's a 1 that's sitting out there. So this is 5 minus 1, so 4 root 6, and then that's it. Okay, now this next one, I don't have like terms, so I want to try to simplify here. I know that 12 is 4 times 3, and so the root of 4 is 2, and the root of 3 is just root 3. And I'm going to bring this down, so I get 2 root 3 plus 2 root 3, which is 4 root 3. And we'll do the same thing with number 4. I don't have like terms here, so I want to simplify root 45. That's going to be 9 times 5, so the square root of 9 is 3, and root of 5 is just going to stay. And let's bring everything else down. 15 root 5, and then be very careful, there's a minus here. So 15 root 5 minus 3 root 5 is 12 root 5. Let's go ahead and turn the page. Okay. Next, we're going to multiply and divide. It says, note the phrase that pays, inside to inside, outside to outside. Sing it to yourself. It's fine if you don't sing it. What we're going to do here is we're going to multiply the outer numbers together and then multiply the inner numbers together. And you keep the two parts of the answer separate, the outside numbers together and the inside numbers together. And then simplify the final answer if needed. All right, so let's see what this looks like. All right, so I want to multiply these together. And you've done this before. This is like if you had, 3x squared times 4x cubed. You would multiply the 3 times 4, you would multiply the x squared times x cubed and get 12x to the 5th, right? So this is kind of the same idea. You're going to multiply the coefficients together and then multiply the roots together. So we're going to multiply the coefficients. I'll just write it like this, 2 times 7, and then we're going to multiply the roots together. We're going to say root 5 times root 3. So we're going to get 14 here, and then the roots that I multiply here, they don't cancel. They become one root together. This is one of the properties of roots. And so then this becomes 14 root 15. And there's my answer. So this is the part that can be confusing, just like with rational expressions. When I'm multiplying, I can just multiply everything. I don't have to have a common or like term. So for number 2, I have 5 times 1, which is 5, and root 14 times 2, which is going to be root 28. And then I know that 28 can be factored, and it has a perfect square of 4 as one of its factors. And then I want to simplify here. The square root of 4 is 2, and the square root of 7, I need to multiply and finish this up, 10 root 7. Okay, multiplying, you can multiply anything you want. So it doesn't matter that they're not the same. They don't have to have like terms. I just multiply the coefficients together and I multiply the roots together. 3 times 12 is 36. Oh, the root of 36 is 6, and so then my final answer doesn't have a root in it, and I just get 12. All right. Number 4. Okay, so just like when multiplying, you can combine the roots together like we did up here. Right here. You can do the same thing with the division. Okay, so if I just think about the coefficients that are here in front, I've got a 1 on the top and a 3 on the bottom. Right? There's a 1 that's implied but not written. So I'm going to write that as 1/3. And then I can take the roots, the 2 roots, and I can combine them into a single root, 21/7. Okay, we know that 21/7 is going to be 3/1. Okay, well, so I have 1/3, and then I can take this big fraction and I can break it apart into √3/√1. And we know that √1 is just 1. So my final answer here is going to be √3/3. And write it as a single term. Number 5 is the same as all these other problems here. We're going to multiply the coefficients together and the roots together. 1/2 times 8 is 4. 8 times 5 is 40. I know that 40 has a factor, that's a perfect square. And so I get √4, which is 2. So this is going to be 8√10. Okay, so number 6 is similar to number 4. I've got my coefficients here. I'm going to just write that as 2. And then I can combine these into a single root. If it helps you to write that as a fraction, 2/1, that's fine. Okay, now be careful with this root part. 2 goes into 32 16 times. So I'm going to get 2 times the square root of 1 all over the square root of 16. So that's going to just be 2 on the top and 4 on the bottom, and then I reduce. Okay, last thing is something called rationalizing. Rationalizing means removing the radical from the denominator. So it's kind of not proper to leave a root in the denominator. It's not really proper to have your final answer have a fraction under the root. And so we rationalize by removing the radical from the denominator. So we multiply both the top and the bottom of the fraction by the bottom radical to get rid of the radical on the bottom, and then simplify if needed. Now, you probably already know how to do this, but we're just reviewing. Okay, so I'm going to multiply both the top and the bottom by the denominator, so √7/√7. Think about what that is. This is really just 1. So if I'm multiplying by 1, I'm not changing the value of the fraction, I'm just changing the form that it's in. Okay, according to the properties, I can multiply across the top. √6 times √7, 6 times 7 is 42. And then on the bottom, √7 times √7 is √49. Well, √49 is 7. And so this is the whole point, is to get rid of this root in the denominator. Okay, now you might be asking, can I reduce 42 and 7 are both divisible by 7, but I've got the radicand underneath the radical, and then I've got a constant that's just by itself. So these are two different types of numbers, so I cannot simplify. Okay, I cannot, I'm just going to make myself a note here, cannot simplify further. So don't reduce that. All right, let's try this next one. So this is like saying root 15 over root 2. I don't want to write that as a decimal. We're not working with decimals inside the roots. So I'm just going to break it apart into two separate pieces. And I'm going to multiply the top and the bottom by the denominator, because I want to get rid of that root in the denominator. So 15 times 2 is 30. Root 2 times root 2 is root 4. And so that's going to be root 30 over 2. And I'm thinking about, can I simplify root 30? Well, root 30 is 15 times 2, and neither one of those have perfect squares that are factors. And so then I'm done. And just like number 1, I cannot reduce that any further. I cannot divide by 2. Okay, last problem. We want to rationalize the denominator, so we're going to multiply by the square root of 6 over the square root of 6, multiply across the top. I cannot combine these. These are two different kinds of numbers, and so I have to just put them next to each other and say 2 root 6. In the denominator, 6 times 6 is 36, and the square root of 36 is 6. Okay, now these two numbers that are outside of the root, those two numbers can be reduced. And so I can reduce that and call this root 6 all over 3. Okay, so that is it for today. I hope that helps with your reviewing of radicals and simplifying. See you later.